All right, here we go. Um, so this is gonna be the first video for my YouTube channel, nonboi-nary. I tried to do this via live stream, but apparently you have to wait 24 hours with YouTube. Um, so anyway, the idea for this channel is like I've basically studied computer science and math in college, and I now work as a data scientist at a company, and I've been working there for 5 years. Not necessarily always doing the projects I want to do, um, and I've definitely developed my skills as a developer, but I want to get better. I see all these people out there on YouTube who are really good at what they do, and I want to get better, but I never push myself to actually do this stuff, to do the work, because I just want to be the best at everything without having to try. Um, so, what I'm going to do with this channel, hopefully, is keep myself honest by routinely posting videos, um, and hopefully, you know, get some help, feedback from other people who may start watching. Um, I'm a normal dude. I've never been the smartest or the best at anything. Um, Probably because I don't work as hard as other people. Not to say that I don't work hard. It's just, yeah, I don't know. I don't know how to put it. But anyway, you can see here I have my terminal open. We are making a little toy search engine in Rust. Now let's see if this will build. Cool, it will. And let's see if it'll run. Um, so right now I basically have it printing an inverted index for some sort of data set that I downloaded from Kaggle. Um, you might notice that the project name is called Coil. So there is this new paper out. Google coil embedding search. So uh, there is this new paper out that I heard about, uh, where it's basically kind of taking a new approach to search engines. Um, and the thing is that most of the time when you're working with a search engine, for those of you who don't know, basically what you do is for all the documents you want to be able to search over, you split the passages of text into smaller units of text that we call tokens. Um, and then basically you go ahead and create some sort of, it's not like a relational database, but it's some sort of storage system where um, each token maps to a list of documents that contain that token. And this is really fast and efficient when it comes to searching. Because basically, all you have to do is kind of like an O of one lookup for each token to find all the matching documents. And then once you find all those matching documents, you just have to score them and sort them. Um, so that's like classic lexical match search. Um, Now, the problem is, uh, you might have a big web search engine like Google, and someone searches for bank, and that could potentially have different semantic meanings. So, a bank in one context is a place where you put your money, but it could also be the Bank of a River, which, can be very confusing for these lexically based search engines to pull up results for. Um, so, I don't know, my history is going to be wrong on this, but basically, with the advent of neural networks and these large language models, um, what people have been drifting towards more in the search industry is, instead of using something like classical lexical search, which is really fast, we have these neural networks that can take in large amounts of unstructured data and produce these embeddings or vectors that encode the semantic meaning of a passage. So, if I was working on something like a job search engine, I might have a nurse job with a nurse job description. I might have a doctor job with a doctor job description. I go ahead and feed those into my neural network. That outputs an embedding. And then I can go ahead and compare those two embeddings to each other to see how semantically related these two job descriptions are. And the idea is that if you have a corpus of documents, you can go ahead and generate an embedding for your query and search it across your corpus, doing a process called ANN, short for approximate nearest neighbors, for which there are a variety of algorithms for, but basically your index looks a lot different. And it's a lot less efficient because basically you're storing the entire vector for a document, as opposed to just kind of like having tokens map to the IDs of documents, which could be, really, really small, or like having like one float for each token that's matched in a document. You know what I'm saying? So those can be really slow, and that idea is actually is outlined in this dense retrievers diagram. Let me make this bigger. But what I kind of wanted to look at was this thing called COIL, which basically, I think like the downside to this dense retriever approach is that it doesn't necessarily account for the fact that, two things might be super semantically related, but it doesn't account for any of the exact lexical matches of two documents, and that's one aspect of it, which, from like a relevance perspective could be seen as harmful to users. It's like much harder to explain what's going on with this dense retrievers approach. And also, this like ANN search can be incredibly memory inefficient. So the idea behind COIL is like, what if we take something that's even more memory inefficient, but like I think like a little less hard on your CPU, that still uses the same inverted index architecture. So the idea is that these transformer models, they produce an embedding for every token that's in a passage, and one of those tokens is the class token. Now, the class token represents the semantic meaning of the entire passage, but you actually have embeddings for each one of these little tokens here. So what COIL is trying to do is say, hey, instead of just using the passage embeddings, what if I also compute the similarities between query token embeddings and document token embeddings if there's an exact lexical match? So what this kind of does is it kind of imbues this lexical matching approach with the capability of avoiding these scenarios where there's a semantic mismatch, like bank versus bank. However, if you only do this, you run into this issue where, like, let's say you're searching for attorney jobs, and the job title might be lawyer or something. That's what we call a vocab mismatch. The words have the same semantic meaning, but they aren't the same word. And so you still kind of need this dense retriever approach. So that's what I wanted to look into. And let me show you guys what I have so far. Just need to hit the vape real quick. Man, do I have any charisma? Probably none. Probably none. I doubt anybody's going to watch this. I got roasted by an 11-year-old today. I was like playing basketball with these kids, and I showed them my beats, and they were like, "This is trash. This is garbage. I would never listen to this." I would like maybe listen to it once as like a troll thing, but never again. Yeah, it kind of hurt my feelings, but what? We're good. We're good. We're moving on. We're moving on. Okay, so here's what we're doing. I basically built this index data structure. I go ahead and load a CSV, build a reader, blah, blah, blah. I'm going through each record in the reader, giving it a doc ID using this enumerate on the records iterator, going ahead and extracting, I guess this variable is called title, but it's actually the description of a job, tokenizing it. I'll get into how my tokenization function works later. It's not that special. Probably something we'll beef up in a later video. And then we're going to go ahead and I don't know how long this recording is. And then we're going to go ahead and basically create an ID for a token, and index this, I guess like the term frequency for that token in this document. Yeah, that's pretty much it. Plain and simple. I already showed you a working example of that, so let's go ahead and check out the library, shan't we? Okay. So, what are we working with here? I want to go ahead and reorganize this a little bit. Okay, so we have a really basic stir hash function. I don't remember why I made this when, like, this is basically like what the inside of a hash map is doing, and I'm already storing these token IDs in a hash map, but let's move on. The tokenize function. Yeah, so what are we doing? We're basically just doing something really simple here. We're taking out all the new lines from a string. Probably could use a regex here or something, splitting on white space and turning everything into lowercase, and turning that basically into a hash set of strings. Cool. So now I created this new data structure called a score vec. It's basically storing a bunch of scores. It has a stride, it has a size, and basically the idea of this thing is, you know, we want a 1D array where, you know, we could have a vector, right? And this basically would like represent the like token embedding of a within like a certain document. So let's say like, whoops. So this is doc 1, doc 2. You know, storing this in a 2D array, based on my understanding, is just very inefficient. Like, you'll basically have two pointers pointing to different parts of memory, and we're not really taking advantage of cache locality here. Whereas if we go ahead and turn these into a single dimensional vector with stride, basically like what the stride's going to do is, we're going to go wee, and that's when our next entry starts. Whee! Did you feel? So yeah, I'm not really doing anything with these like token vectors right now. They're basically just gonna have size 1, so this shit is kind of really unnecessary. So yeah, that's cool. Yeah, got a little implementation for this here. Don't want to dive too deep into this. Pretty simple, straightforward stuff, you know. Okay, let's go ahead. Hit list. So hit list is basically going to have a vector of doc IDs and a score vector. And basically what we want is something like I was showing in this comment up here. This is basically like the visualization of a hit list. And we will basically have one of these per token. Cool. So then we actually have our index. So normally search indices like these need a few things. So the first thing is the inverted index, where we go ahead and map tokens to lists of documents. The next thing we need is something that maps documents to their original source content. So that's the forward index. So that's why we have these two hash maps here. Inverted index takes us from token ID to hit list. And you know what? I should probably just do type toke ID U64. Does that work? I'm new to Rust. I'm relatively new to Rust. Does this work? Okay, cool. Boom, 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 boom. Okay, perfect. And let's go ahead and try to replace references of this everywhere. Sorry, I'm getting a little sidetracked. Just doing some cleanup. Yeah. ASMR coding. I don't know. Do you guys ever watch any of that? There's no chat for me to talk to. I'm basically just talking to myself. Weird. It's weird. It's weird. It's weird. Probably also want to create a type doc ID equals new size, and that will at least make it more clear. Doc ID. Okay, let's see. Toke ID and doc ID. Okay, cool. And we should probably dive into like what I've done with regard to indexing. So let's just talk about this function for a little bit. So what's going to happen is we're going to go ahead and tokenize our document first. Right now this is happening in the main loop, but we probably want it to happen somewhere else. Maybe I lost audio there for a second, but I'm going to just repeat what I said. So we're already tokenizing our documents in our main loop because that's where we're iterating through them. So basically what we're going to do is for each token, we're going to add our document to the hit list. So, you know, we're going to take our token ID, we're going to take the doc ID, we're going to take our scores, which is basically some sort of like term frequency, how many times the document is, or the token is in the document, and then go ahead and add the document itself to the, what's the word? to the forward index. But let's go ahead and look at this. So we look at inverted. We see if the token ID already exists. If not, we create a brand new hit list. Once we have a hit list, we add a document to that hit list. We also add an entry to the forward index. We increase the number of documents, we return OK. Cool. So here's the next part, and this is the part that I want to do with this video, which is like actually implement a search function. So I don't know how we're going to do this. Fuck. Can I turn on music? But it has to be royalty free. I don't want to deal with that. Okay, we're not going to turn on music. So here's what we want to do. Is like the first thing we want to do is we want to get the hit lists for all our tokens, right? So, we want to get the hit list for all our tokens, but we also want to calculate the document frequency. In other words, like how rare is this token? Because basically, like the basis of our scoring function for ranking documents in a search is going to be the number of times the token appeared in that document times how rare that term is. It's a pretty good way to get a decent search engine. So what am I doing here? I'm getting all the tokens. I'm creating an array of float 64s. These are going to be document frequencies. Getting the token ID, getting the hit list. If the hit list has any documents, I'm going to go and get them. Otherwise, I'm going to return an empty slice. Okay. So the thing is we have to accumulate scores for our documents, right? We have to accumulate scores for our documents. So one like sort of memory inefficient idea is basically if we know the size of the hit list, we can basically create a vector. That vector basically stores something like how many tokens were matched, the term frequency, but it would be nice to know like what tokens were matched to, like, or in other words, like we're gonna have all these hit lists, and I kind of need a way to say that for each document, here's the number of hit lists it hit, and here is the score for that. And these hit lists aren't sorted, which, is probably like another optimization we can make later. So basically, I'm wondering if what we need is to pre-allocate something like a dict for each doc. We don't want it to be the size of our corpus, because if there's like millions of documents, it's not going to work. Man, see, you guys are watching the rubber hit the road. I'm straight up shitting the bed here because I don't know what to do. But we'll figure it out. That's how things work. It's 11:42. I have to go to the gym tomorrow. Fucking hungry. Should I DoorDash something? Maybe I'm gonna DoorDash something. Those tacos weren't good. Wow, there's not a lot of healthy stuff to order. Maybe I'll just get a burger and a Diet Coke or something. Let's just do burger and fries. Done. Okay. 23 to 30 minutes. Jesus Christ. These service fees are insane. And I'm even a Dash Pass member. Okay. So I'm just trying to think about this again. And we should probably try something, right? One way to do this, and this is like kind of like a brute force approach, is we basically create some sort of hash map of doc ID to like a score like accumulator. And then what we'll do is whenever we go over these hit lists, we'll basically, what's the word I'm looking for? We'll add stuff to the accumulator. Like we'll add an entry, and if one already exists, we'll just go ahead and add like the TF-IDF score. Like that's probably like the easiest way to do this, right? Now, right now, I am basically just getting the document list. I'm not even getting the like score vectors or whatever. So that's fine. We don't need those score vectors right now. We're basically going to treat like the term frequency like it's 1 if the token appears in the document any number of times, which isn't great, but you know, it's better than nothing. Yeah. I'm going to go ahead and modify this too. So what we'll do is we'll make the description a searchable field, and the title the field that actually goes into the forward index. So let's go ahead and do description, or sorry, title. And really what we should be doing is doing the for loop in here, but I'll deal with that later. Okay, cool. So yeah, I'm thinking the hash map approach probably the best way to do this, but you know, we could just, I don't know. It's probably the easiest way to brute force this for now, and if we want more performance, we could think of a better way later. Okay, cool. So let's do this. We're gonna do let mute score equal, and it's gonna be a vec, or no, it's gonna be a hash map of doc ID, and let's just say float 64. Yeah, okay, cool. And new, oh man, I'm treating this like it's fucking Go, aren't I? Right. Oh, whoops. I should probably put this here. That's just the type signature. And then we will just infer that. Yeah, and we're gonna have to make it mutable because we're gonna add shit to it. Okay, cool. So basically what I want is to, we have the docs. So for doc ID in hits, and we could probably turn this into a map instead of a loop. What we're going to do is scores dot entry what happens when you have a hash map of float? Hash map float values initialized rest. Okay. No. Okay, you know what? We'll just figure it out. You guys are also watching me look through docs, but entry gets the keys corresponding entry for a thing in the map. Okay. And then let's do doc ID, and then let's do dot or insert okay, insert with takes a function. Insert with key, I think we're going to, this is probably what we want, and we're going to put 0.0. So basically, if a doc isn't in there, we're going to put 0.0, and we're going to let this be doc score equals this. And this should be a mutable reference, right? Why do I have to dereference? Oh. Why do I have to dereference the borrow? What the fuck? Okay. Do I want this? Okay, yeah. Well, I guess it's because it would move the key into entry because this is rest. And basically, if you, even for primitive types, like this is what I like about Zig, is that primitive types, they move, but they don't, more or less. I think it actually is copied by default, unless you're like using a pointer. But in Rust, they move. So, and let's do doc score times equals, is that how this works? Doc freaks I. It's going to complain. If I dereference, okay, I have to is this returning a pointer? It's going to complain. Will this build? Holy fucking shit, if this builds, this will be sick. But I have to remember the TF-IDF formula. We don't necessarily want the actual document frequency. We want something like, okay. We're using a Boolean frequency. let's see. So we actually, let's do a probabilistic one. So we're gonna want log. Okay, and we also want size log. Okay, yes. So we want this log. It's unsafe. Okay. Okay, we want that instead. So I don't know what makes it unsafe. I don't like to dive deeper into things. Can you tell? I'm an idiot. I'm stupid. Okay. So then we're gonna want to do this by doc. I think we want doc freaks. Oh wait, doc freaks is not. Let's just get rid of this. So what we're gonna want, and let me just get rid of this too. So what we're gonna want is the size of the corpus minus the number of documents in the hit list. Over, wow. It would be nice if there was a way I could avoid a division here, but that's fine. And we also want hits.len in the bottom. I don't know if I want to call hits.len twice. Let's just do let doc freak equal hits.len doc freak over and then we want over doc freak. Cannot find value. Oh yeah, and we want this as F64. And that okay, cool. And so I guess we don't need this enumerate anymore. Whatever, and I think we can just do for token in tokens. And do we want to put the borrow here? Yeah, so we're borrowing a slice, whatever. Cool. Okay. So now we have our document scores. And so we've gone through all the tokens, we've accumulated all the stuff, and we're not gonna really like care about how many tokens were matched. Normally that's something you would care about. I think because, you know, like let's say you have a 2-word query, you don't want matching on a single rare word to overcome the fact that like another document matched both words. I guess that's not actually possible with our current setup. But, you know, in a case where we actually had like actual term frequencies, it would matter. So yeah, so we want to score scores by its value, by the values. Like we basically want to sort one array by another. So scores dot values dot zip dot sort. How do I sort something? Sort. Merge sort. No. Scores dot sort dot values dot zip scores dot keys dot. Okay. I don't know Rust. How to sort Rust hash map keys by values. Okay. Do I need to collect this into a vector and then sort? This is already an iterator. Dot. Okay. Well, scores dot iter dot swap. Okay, so man, and then okay, dot collect. Let items vec equal. Okay, let's see if I will get a completion. Dot sort by this is stable sort. Okay, sort by key. Let's see some examples. Okay, so we're gonna take two values, which is the TF, IDF, and the doc ID, and then dot, and then we're going to return tf idf, and then oh, I think I need to put, do I need to put, the trait bound f-ord is not satisfied by the following types. Okay, we'll just find this out when we do the compiler stuff. Uns. You know what, let's just... Okay. Okay. Here we declare foo with the trait bar method. T is a foo, so that means T must have bar. Okay, 5i32, the trait bound to i32 foo. Okay, so is this basically saying that float 64s can't be ordered? That's knucking futz. That's hilarious. Man. See, I normally code in Python all the time. So this would be quite a trivial operation. But it's cool. We're learning something new. What is it even? What if it even is items? You're not telling me what it is. No, we definitely want sort by key. Okay, and we're gonna have, whoops, we don't want scores dot editor, we want scores dot keys. Okay, and then we want value, tfidf, and doc ID, and we're just gonna return tf idf. What if I do doc ID? What if I just sort them by the doc IDs? Cannot borrow items as mutable as not. Okay. So it doesn't want me to I have a reference to a reference of float 64. And I want to sort by value. Okay, takes 2 arguments. Fuck me. The trait... Okay. Okay. So that's cool. The issue is I don't have partial comp. I don't have partial comp. Um, um, what if I wanted to use sort by key? By key, a vec. Okay. So I think that's what I want, but let me just see. Does that take immutable? No, it just takes a self, and then it takes an other, which is another reference to, and it outputs an ordering. And then we're going to return self dot partial comp other dot unwrap, and let's just see. This is probably not what we want to do. Is panic. Dude, you know what F64 is. You know what F64 is. Come on. Do I have to do this? Okay, I am referring to it directly. It's from the standard library, okay? Okay, so I can't... That's fucking hilarious. So, how do I sort a hash map of float 64s? See, I totally didn't read this. You're looking into the beauty of how stupid I am. So, Okay, so what we want is there's going to be a doc ID, and then there's going to be a TF-IDF. Or there's going to be hit A, hit B. And what we're going to want to do is something like hit A dot 1 dot partial. Oh, yeah, and this is going to be a vector of what's its doc ID F64, and then okay, yeah, no shit. Oh, we don't want sort by key, we just want sort by. And this is going to be hit A dot 1 dot partial comp hit B dot 1. Do I want to unwrap that? Okay, yeah, I do want to unwrap that. Whew. That was painful. That was painful. Okay. And I think let's do n or num hits size, and what we want to do is items dot up dot first mute fill first. Is there like a dot up to, or when can I okay, this is gonna return a slice. And I think we're gonna do up to num hits dot unwrap. Well, actually, wait, dot unwrap will this work? Okay, and I have to borrow this, or do I have to borrow this? Food's here. I gotta charge up. Boo forgot to take her vape. She's going to be sad. But maybe not really. Maybe she can quit smoking. Fuck. Oh, shit. But I lose my monitor if I... Damn it. Okay. Will that work? Okay. We're at least not dying. Cool. Okay, we're back in it. So... This needs to return a slice of I'm sure I'm gonna run into like a lifetime thing, because basically like the data that this is referencing is all going to go away. Like, okay. The thing is like the reference to the doc IDs is gonna live as long as this index is alive. But the score is only in the scope of this function. So unless that score is like moved out of here, you know, this shit might not work. So we'll see. We'll see. What is this gonna be? Required by a bound. Right. I think if I do a dot into iter, that should work, and this should not. Okay. I knew this was going to happen. I didn't know this was going to happen. I work in garbage collected languages all the time. I just take it for granted, man. I just take it for granted. I am both hungry and tired, and have been doing this for an hour. Like, literally just something so simple. But that's the beauty. That's the beauty of this channel. This is what we're here to do. We're here to suck. Okay? I've spent my whole life giving up when things get hard. I think tonight is probably not the best choice. You know, given I have to go to work tomorrow, gym. It's fine. It's fine. So what are we gonna do? We need. First of all, we want the reference to the doc IDs to come outside. And we want to move the float 64s. We want to like move the reference out of here, and it's going to contain reference. Okay, so my compiler's complaining. Whatever, it's fine. So let's just go to into. Okay. Now, can I call collect on this? Okay. I think I get what's going on now. So, yeah, and this is important too. So I think basically what's happening is that, you know, the hit list owns the doc IDs, right? But here I'm getting a reference to those doc IDs. And when I'm calling entry, what I'm actually doing is copying the value from the reference into the scores hash map. So now there's like a newly allocated entry. And so this hash map owns a copy of the doc IDs in the hit list, right? Because we want the index to still keep around the doc IDs, but we might need them later. Now, like, the thing is this might not be the most efficient way to do it. We might just want, like, the references themselves to, like, actually be the keys, but we're still allocating new memory, right? Like, it's still basically just like a pointer. Like, you have to put something on the heap for this hash map. It's not like using a reference here does anything. So, okay. Borrowing what? This argument? Does that even work? Yeah. Fucking shit, it does. I guess we don't want to move. We don't want to move this into here. Okay. Right. The scores is, a local variable to this function, and we need to move it out. We need to move it out. Wow. Gorgeous. Gorgeous. Okay. I didn't even need to do that. Okay. Let's try something like this. Let's let query equal software engineer, and then let's do index.search query query, and it's gonna say, oh, it's already a stir. So let's do this. Let results equal index.search query, and let's just print results. Query let's do query please. Okay. I forgot to do the forward index lookup. Was that weird? Was that weird of me? Am I just being weird? Is it just midnight and I'm being weird? I'm being weird. I'm being fucking weird. Okay, yeah, but that reference isn't owned by this function. It's owned by this struct. So as long as the struct's alive, we're good. We don't want a mutable reference. Okay. Um, hmm? Right, I forgot to unwrap this. Always got to handle the null values. Come on, man. I guess it's a reference to a string. But it doesn't like this. It doesn't like this. I'm not... Okay, so what I want to do is I want to just apply this to like one of the values, right? So that should do exactly what I think it's doing. Should it not? I'm returning a tuple. Fuck me up. Okay. It is powerful. You know, it's powerful when it fucking works. I'm not even talking anymore. I'm not even talking anymore. My head is hurting. It's 12:38. Was this a successful video? I don't know. But we never give up. And I'm going to keep doing this. And if I don't, I'll have a video proof that I didn't stick to my word. So, pow, pow, pow. Yes, yes. All right. Well, thanks for tuning in. If anyone tunes in, talk to you guys later. Bye.